Explain the video goal and say this will cover what a satellite is, main satellite types, the basic subsystems that make satellites function, common orbit families and why they matter, typical mission roles and applications, the ground segment and operations, design and testing trade-offs, space safety and regulatory issues, and safe learning paths for students and engineers. Give a simple definition of a satellite as any human-made object placed into orbit around Earth or another body to carry instruments or payloads that perform communications, sensing, navigation, science, or technology demonstration tasks. Describe common satellite mission types at a high level. Earth observation and remote sensing for mapping, land use, agriculture, and disaster response. Weather and climate monitoring to track clouds, storms and long-term climate signals. Telecommunications and broadcasting to relay voice, data and video. Navigation and timing constellations that provide positioning services. Scientific missions that study space, planets and astrophysics. Technology demonstration and in-orbit servicing missions. Space situational awareness and debris monitoring. Introduce orbit families in plain terms and why they are chosen. Low Earth orbit LEO for high-resolution imaging, low-latency communications and small satellites. Sun-synchronous orbits for consistent lighting and Earth observation. Medium Earth orbit MEO for navigation constellations. Geostationary orbit GEO for fixed coverage of a large region, ideal for broadcast and weather satellites. Highly elliptical and polar orbits for long dwell times at high latitudes or special coverage. Explain basic trade-offs, altitude affects coverage area, revisit time, latency and launch energy. Outline basic satellite subsystems conceptually. Payload that performs the mission, such as cameras, radars, transponders or scientific instruments. Bus systems that support the payload, power system using solar arrays and batteries, communications and telemetry for command and data transfer, attitude determination and control to point instruments and antennas, onboard computers and software for control and data handling, thermal control to keep components in safe temperature ranges, propulsion for orbit insertion and station keeping on some satellites, and structure and deployment mechanisms that hold everything together. Explain how satellites communicate and move data. Telemetry tracking and command TTL. Mission data downlinks transfer payload data to ground stations or via relay satellites. Data is processed on the ground or sometimes on board for real-time products. For constellations, inter-satellite links may be used to route data across the network. Describe how satellites are placed into orbit in general terms. Launch vehicles deliver a satellite to a target insertion orbit. Some satellites have onboard propulsion to raise or adjust orbits after separation. Constellations are deployed with planned phasing and spacing. Emphasize that launch and orbital insertion are complex operations handled by specialized providers and regulated authorities. Cover operations and mission lifecycle conceptually. Commissioning after launch checks health and calibrates instruments. Routine operations include attitude control, power and thermal management, scheduling of passes with ground stations, data downlink and processing, orbit maintenance such as station keeping burns where applicable, anomaly detection and recovery, and end-of-life disposal or deorbiting according to guidelines. Discuss design trade-offs and constraints at a high level. Mass and volume limits drive payload choices. Power budgets constrain instrument duty cycles. Radiation environment and thermal extremes influence component selection and shielding. Lifetime goals and reliability drive redundancy and component qualification. Cost and launch availability shape platform choices from small CubeSats to large geosatellites. Explain testing, verification and qualification without procedural detail. Satellites undergo environmental testing for vibration and shock from launch, thermal vacuum testing for the space environment, electromagnetic compatibility checks, software validation and mission simulations to ensure performance before launch. Talk about space safety and regulatory considerations. Frequency coordination and licensing for communications must be secured through national regulators and international bodies. Space debris mitigation guidelines encourage passivation, controlled re-entry, or moving to graveyard orbits for GEO. Responsible operators follow tracking and coordination practices to reduce collision risk and support space sustainability. Mention commercial models and constellations. Explain that many modern services use constellations of small satellites for broadband, Earth imaging, or IoT connectivity. Business models include subscription services, data licensing, hosted payloads, and government contracts. Address data, privacy, and policy topics at a high level. Remote sensing and communications intersect with privacy, national security, and export control considerations. Operators and users must comply with laws and coordinate with regulators for sensitive capabilities. Visual suggestions for the video input.